A-Level Paper 1, Specimen Set 2. Now, you possibly remember that water molecules are small, water ligands are small, ammonia ligands, NH3, are small, but CLs are big. So it says, write a reaction of hydrochloric acid. You know hydrochloric acid is a strong acid, fully dissociates from H plus and Cl minuses. Well, the Cl minuses have got lone pairs of electrons. You can form coordinate bonds with the central Fe. But you can't get 6 Cls around an Fe. You just can't fit them in. They're too big. So you only get 4 around it. So let's work out what the charges are. If it's Fe3+, the Fe is 3+. Water's a 0, so there's 3+ overall. The Cl is -1 charge. After all, Cl is in group 7, wants to gain 1 electron, so they form Cl minuses. And it's come from HCl, H plus Cl minus. So chloride Cl minus, 4 of those. If it's Fe3+ and 4 Cl1 minuses, there's 1 minus left over. It's got a charge, it's going to dissolve. If it's got no charge, it's a solid. If it's a charge, it dissolves. That's actually green. H2O's come off. Okay, so something to work out. You can work that out. Why is it going to have a different shape? Well, this is going to be octahedral with 6 ligands around it. Here, 4 around it. It's going to be tetrahedral, so it's going to change shape. Bond angle 90 down to up to 109.5, going to tetrahedral. Why does that happen? Cl's a bigger ligand, so only 4 Cl's can fit around the transition metal ion around the Fe3+. Fe accepts 6 ligands around itself by forming 6 coordinate bonds. Hexacyclic requires, this is the 1,2-diamino ethane, NH2, CH2, CH2, NH2. It's a bidentate ligand. So 3 of these are needed, only 3 of them, because they can form 2 coordinate bonds each. Instead of the 6 waters forming 1 coordinate bond each and being monodentate, the coordination number still stays as 6. I only need 3 of these around the Fe because each of them forms 2 coordinate bonds. And I've drawn it like that. It could be better. Instead of the corners, I've done the skeletal form with the CH2, CH2 there. I've just simplified it. You could put CH2, CH2 there. I could make it better, actually. This is from the mark scheme, and I think it's quite poor, actually. I would prefer to see a lone pair of electrons on each of those ends and show the coordinate bond. They're being donated in a coordinate bond by doing an arrow down to the Fe from those 6 coordinate bonds. It's 2+ charged overall because the it says hexa-aqua ion 2 this time, so the Fe is 2+ charged, and these ethane diorates have got no charges. Let's look at the next one. Hexa-aqua ion 2 react with an excess of this 1,2-diamino ethane in a ligand substitution reaction. We've just seen that. What happens to the entropy change? Well, all you've got to do is count the number of molecules on the left and right. 1 and 3, 4 molecules on the left, making 1 and 6 on the right. So there's 4 molecules on the left and 7 on the right. Fewer molecules making more disorder. More molecules means more disorder. Just like, say, for example, if I took a piece of paper and there's 1 piece of paper and disordered it by shredding it into lots of little bits, fewer molecules, fewer bits, making more molecules, more bits, more disorder. 4 molecules make 7. That means there's more disorder. The entropy is positive. That was the 3rd option down. Iron 2 sulfate 9 tablets is determined by titration with potassium manganate 7. You've got to learn what potassium manganate 7 is. Manganate 7 is MnO4, and K plus potassium manganate, K plus MnO4 minus. So when potassium manganate 7 dissolves in water, it makes MnO4 minuses, manganate 7 ions. It's in acidic solution because it reacts with things like Fe2+ and oxidizes them into Fe3+. When it oxidizes, the Mn, which is in oxidation state +7, plus 7 minus 2 minus 2 minus 2 minus 2, or minus 8 from the 4 oxygens minus 2 each, is minus 1 left over. It goes down to oxidation state plus 2. So it's reduced from oxidation state plus 7 to plus 2, and as that's reduced, it oxidizes the Fe2 plus into Fe3 plus. It's an MnO4 minus. Manganate 7 is an oxidizing agent. It's purple, and the MnO2 is colourless. That's why you can use it as an indicator, because it keeps reacting and forms the colourless Mn2 plus. But as soon as the Fe runs out, then if you had this potassium manganate 7 in a burette, then the purple colour would come through the burette. There'd be nothing to react with because the Fe2 plus would have all reacted, so it wouldn't go colourless and form Mn2 plus. Some of this would run through without reacting, then not able to react, and would form a purple colour in the bottom of the conical flask. I need to do half equations probably to work out where the 5s and the 8s are coming from. I know that the Fe2 plus gets oxidized by this oxidizing agent manganate 7 to Fe3 plus. Half equations, I'll need an electron, I'll need it on the right so that I've got 2 pluses on each side. MnO4 minus makes Mn2 plus. Where can the O's go to? Well, I can use H pluses and waters from my toolkit to balance half equations. So I'll make some waters on the right hand side, so I've got somewhere for the O's to go to. I've got 4 O's on the left, so I'll have 4 O's on the right by putting 4 in front of the water. That gives me 8 H's. I'm going to put 8 H pluses there. Remember, in my toolkit I've got H pluses and waters. 8 H pluses. Now I've got to balance the charges. I've got 1 minus there and 8 pluses. I've got 7 pluses on the left hand side. I've got 2 pluses on the right hand side. I need to get both sides down to 2 plus to balance up the pluses. 7 pluses, so I need 5 electrons. 7 plus and 5 minus leaves 2 pluses, 2 pluses on each side. Now if I combine the two, I need to multiply the top equation by 5 to get 5 electrons on each side to cancel. So I have 5 Fe2 pluses, MnO4 minus stays the same, 8 H pluses stays the same, Mn2 plus stays the same, 5 Fe3 plus because I've multiplied this top equation by 5, and my electrons will cancel, and I've got 4 water.